We're back with 2011 CCEA Physics A2 paper, Unit 2 Fields and Their Applications. And question 6 is about charged particles in electric fields. Part A proton enters the uniform electric field between two horizontal plates. It enters horizontally with a speed V0 of 4 times 10 to the 5 meters per second. And figure 6.1 illustrates the situation. So you can see we've got here, we've got a positive plate and negative plate. We've got 80 millimeters between them. They have a length of 120 millimeters, and we can assume that the field starts when they enter these plates and ends when they leave them. So calculate the magnitude of the electric field strength E if the voltage between the plates in figure 6.1 is 148 volts. So this is a straightforward use of an equation from your notes. The fact that the electric field in this kind of situation where you've got parallel plates is simply the voltage over the distance between the plates. So we need to just fill in that equation. E is V over D, and so we have a voltage of 148, and we're dividing by 80 millimeters, which is 80 times 10 to the minus 3, and that gives us 1850 newtons per coulomb. Part 2, calculate the magnitude of the acceleration experienced by the proton if the electric field exerts a constant force of 2.96 times 10 to the minus 16 newtons. The effect of gravity on the proton is negligible and can be ignored in this question. So this is just Newton's second law then. So we've got F equals ma. So A is going to be F over M. So what we need here to go with this force is the mass of the proton, which we can get from the formula sheet. So we put our force value on the top line, and we get this mass of the proton from the formula sheet, and that gives us an acceleration of 1.78 times 10 to the 11 meters per second squared. Part B, then calculate the magnitude and direction of the velocity of the proton on exiting the electric field and state the direction relative to the horizontal. So I'll just bring the diagram back. So it's a proton. We've got positive up here. So it's going to curve down the way because the electric field is down, proton's positive, so the force will be downward. Or another way of thinking about it is it'll be repelled from this positive plate and attracted to this negative plate because the proton is a positive particle. So it's going to come down and it'll exit here with a final velocity because the field will stop pushing on it at this point here, and at that point its final velocity will be established. Now, how does this final velocity come about? Well, remember, this is like a projectiles problem. We have a constant downward force on this proton because we have a uniform field. So it continues to have its horizontal velocity because there's no force in the horizontal direction. It gets a vertical velocity, so the final velocity will be a combination of the original u horizontal added to the final velocity in the vertical direction, and that will give us our final overall velocity. Okay, now annoyingly they called this horizontal u v0, but we'll put that in there. So it keeps that during its flight, and then it gains this vertical velocity because of its time in the electric field. So we need to figure out how long it was in the electric field. How long is it in the electric field? Well, basically, the answer to that question is how long at this speed does it take you to cross 120 millimeters. So that'll give you the time that it was in the field for, and that's the time then that the vertical acceleration acted for. And so you can work out what's going on with your UVAS list for the verticals just by getting the horizontal time. So the time in the field is going to be the horizontal distance divided by the horizontal velocity, and in our case that's going to be 120 millimeters divided by the 4 times 10 to the 5. Okay, so we've got 120 times 10 to the minus 3 divided by 4 times 10 to the 5 to get a time of flight. And that gives us this very small time of about 0.3 of a microsecond there. So 3 times 10 to the minus 7 of a second. And now we can do a vertical UVAS list. So we have an initial vertical velocity of nothing because it comes in horizontal. Final vertical velocity that we are interested in. Acceleration that we got from the previous part. Vertical displacement that we do not know. And vertical time that we've just got from the horizontal motion. Because time links both types of motion. It's doing the horizontal thing for the exact same amount of time it's doing the vertical thing for. So we need an equation that has v in it but doesn't require us to know s because we don't know s. So v equals u plus at, and u was nothing, so v will just equal at here. So we've got 1.78 times 10 to the 11 acceleration times 3 times 10 to the minus 7 seconds to get a final velocity of, well, of this value of 53400, and that's the vertical part. So that's the value that belongs here in this triangle, and so we can get the value of the final velocity here by Pythagoras. So the final velocity value is going to be the square root of v horizontal squared plus v vertical squared, which is going to be the square root of that, and that's going to be this value of 403,548, and 2 3 significant figures we could write that as 4.04 times 10 to the 5. To get a direction we need to get this angle here below the horizontal, and we get that from Pythagoras, or sorry, from trig. Just the tan of that will be the vertical velocity over the horizontal velocity. So theta is going to be tan to the minus 1 of v vertical over v horizontal, which is tan to the minus 1 of 53400 over 4 times 10 to the 5. And that gives us this value. Just be aware that if you're going to take trig functions, you better be in degree mode on your calculator. And you need to be specific that this angle of 7.60 degrees is below the horizontal. So quite a lot to do there, and not an awful lot of space. Of course I took up some of the space with the diagrams and stuff, but hopefully you can see clearly what happened there. And that's that.